In this lesson, we want to look a little more closely at our contrived digital means in the last lesson for communicating the temperature of a temperature sensor over to a receiver or controller by way of lumped values of highs or lows that comprised pulses. So we call these zeros or ones, or low and high, or true false, and we basically just put out n pulses where the temperature scale was maybe 1 pulse per degree C, or if we needed more precision, maybe we said 1 pulse per tenth of a degree C. And we want to consider now how efficient this is and if there's a better way to do this. So clearly, you probably are already anticipating that this is not a very efficient way to count, because if we were sending some data that had to have a value of, say, 100,000, we'd have to put out 100,000 pulses. This would be like if I tell you the temperature is 50 degrees C, I don't start saying the temperature is I do this for, until I get up to, this is 10, this is 10, and eventually this will be 50, right? That's like counting out pulses. So if the value doubles, it's going to take me twice as long to tell you what the temperature is, because I have to draw, twice as many little hash marks. And so what we say instead is I tell you 5, and well, let's do a little different example. Let's say that I had 51 degrees. Okay. So I actually say 50 and then 1. And what I mean by that, when we say 5 and 1, this is 5 tens and 1 ones. Right? And so there's significance to the place, the order in which I give these digits. If we agree that the most significant digit is given first, then when I say 5 1, you know that it's 5 tens plus 1 ones. And we call this place value. So the value is impacted by the position that it has. Now, in the decimal system that we use here, we have digits 0 through 9. So each position in a numerical word, if you will, has a value of 0 through 9, and then there's added meaning by virtue of where it is in the order within that particular word. So let's think about if we can do a similar thing with our digital data. So for digital data, we have lumped values into zeros and ones, right? i.e. just 2 values. And that is not a decimal system where there's 10 digits. This is a binary or base 2 number system. So if we want to use place value, we would have a word, a binary word, that would be comprised of each place value. So these would be the ones and the tens and the hundreds and the 1,000s and the 10,000s, so forth. But I either am going to have a 0 or a 1 here, a 0 or a 1 here, etc. In other words, I can't use digits 0 through 9. So if we have let's go back over to the decimal system. If we have a 3-digit number, or call it word, yeah, okay, let's say three-digit number, how many unique words, words can be produced? Well, if it's 3 digits, then it means it goes from 0 all the way up to 999. In other words, there's 1,000 words that a 3-digit decimal number can represent. In other words, we have 10 to the third, or 1,000 words. Right? If it was 4-digit number, then we would have 10 to the 4, or 10,000 words. So every time we add a digit, we're going to add an order of magnitude of unique words that we can represent with that number. Well, over here in the decimal system, if we have a 3-digit binary number, has, what does it have? We'd count between 0 up to 111. In other words, let's be explicit about this. We'd have 000, 001, 00. There is no 2, right? 1 is the highest digit. So then, just like we get to 9 in the decimal system, we add 1, and so it rolls over back to 0, and we carry 1. We'll do the same thing for the binary system. So it'll be 10, and then we add 1 more, that's 11. We add 1 more, that's like 99. Adding 1 to 99 in the decimal system, that gives us 100. 101, 110, 111. If we count this up, 0, 1, 2, 3, 4, 5, 6, 7. So we have 8 unique words. So 3 digits gets us 2 to the third, or 8 unique words. How many digits, binary digits, do we need to be able to represent a value, or 1,000 unique words? So on the decimal side, we need just 3 digits. Well, let's look at this. If we had 1 digit, let's say number of digits, and then unique words. Make a little table here. So 1 digit, it's going to be 1 to the, or 2 to the 1, sorry. So 2 unique words, 0 or 1. 2 digits, 2 to the squared, that'll be 4. 3 digits, 8. 4 will be 16. You notice you double. So it's different from the binary system. Every time you add another digit, you add a factor of an order of 10, so you add a 0. Here in the binary system, every time you add another digit, you double. So 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Okay, there we go. So it's going to take, so we need 10 digits to represent at least 1,000 words in a binary representation. Compared to 3. Compared to 3 digits in a decimal system. So it's not as efficient, but we can still do it. So now let's go back to our problem up here where we were sending pulses. So can we send a place value quantity or formatted quantity number rather than just sending pulses. Let's consider the case where, suppose, the temp was, let's see here, we'll do 67 degrees. Now, what are we going to send to, we don't want to send 67 pulses, we want to be more efficient about that. So first, how many digits, binary digits, okay, binary digits are needed in order to represent at least 0 to 100 degrees C value. So we need to be able to hold values 0, 1, 2, 3, 4, 5, 6, 7 all the way up to 100. So if we look at our table here, we see that the first entry that has a unique number of words greater than 100 is a 7-digit value. So it will be 7 digits minimally. And there are certain standard sizes of digits that we use. Okay, it turns out that the standard sizes, standard binary word sizes, are 8 digits, and we say bits is what we call them, 8 bits. That's digits. 16, 32, and 64. So instead of using 7, let's go ahead and use 8, just because that's what's standard, though I just want to make it clear that you could use 7 bits in this case. Now let's convert 67 degrees C to a binary word. How would we do that? Okay, so how might we do this? If we go back and look at our table up here, we see that each place value has like the first. Actually, let's not do it this way. So let's return for a moment to decimal number or decimal word. We have the ones, the tens column, the hundreds column, the thousand column, and so forth. So in a binary system, we would have the ones, the twos, the fours, the eights, the 16s, right? Because what we're doing for each successive column is we're multiplying by the base. So when we're doing base 10, we're multiplying by 10. That's why we have the ones, the tens, the hundreds, the thousands. In the binary system, we're multiplying by 2. So the ones, the twos, the fours, the eights, the 16th, 32nds, and so forth. Okay. So what we want to do is we look at this and we look at our number 67 and we say, okay, are there any, the next one after the 64th would be the 128s. Are there any 128s that fit into 67? No. Are there any 64s that fit into 67? Yes, there's one that fits into it. And then we subtract 64 and that leaves 3. So are there any 32s? No, there's no 16s, there's no 8s, there's no 4s. But are there any 2s that fit into 3? Yes, there's 1 2 that fits into 3. We subtract that 2. And that leaves 1. Are there any 1s that fit into 1? Yes, there's 1. Okay, so our number then is 67 base 10 would equal to 100011 base 2. Now let me show you a better way to do this. If we start with 67, we divide that by 2, and that gives us 33 remainder. So this is like the quotient, and this is the remainder. So remainder 1. Then we take 33, divide it by 2, and that gives us 16 remainder 1. Then we take 16, divide that by 2, that gives us 8, remainder 0. We take 8, divide by 2, that gives us 4, remainder 0. Take 4, divide by 2, that gives us 2, remainder 0. Take 2, divide by 2, that's equal to 1, remainder 0. And then take 1, divide by 2, and that is 0 with the remainder of 1. And now we stop. So we stop when the quotient is 0, or after quotient is 0. Okay, and now we read this out. And we read it out as 1, 0, 0, 0, 0, 1, 1. I missed a digit in here, didn't I? Oh, let me go back up here. 1, 1, 1, 2, 3, 4, 5, 6, 7. Yeah, sorry, so there's a 0 and there's a 1. Because I wanted to do an 8-digit representation. 0, 0, 0, 0, 1, 1. Yeah, so there's a leading 0 out here. The 128s would go right here. Okay, and we'll do the same thing here if I want to represent this as an 8-digit value. I just draw that dotted line I like to group them in 4s. Okay, so when you have an 8, this is an 8-digit binary number. Okay, and each digit is called a bit. Okay, and each 4 bits is called a nibble. So, and each 8 bits, or 2 nibbles, is a byte. Okay, so there's bit, nibble, and byte. So, and then typically, although I've used the word lightly for word, when there's a formal use for word, 2 bytes together equals 1 binary word. 1 binary word. Okay, so we use word. So typically we have bit, nibble, byte, and word. And if you go bigger than that, you'd say there's 4 or 2 words is equal to, usually they'll call it a double word. And so this is actually 4 bytes. And we'll stop there for now. So, back to our question. If we want to transmit the value from our temperature sensor, and that value is 67 degrees, and we're going to use an efficient digital means to transmit it, and we want to kind of, just like we say 67, we want to pass or send place value bits down the line. All we need to do is to pass out this 8-digit value. We could do it minimally with 7, but we're going to use the standard byte. So we'll send out 8 values. And so this is what it will look like. If we have slots here, time slots, okay, then we would send this. We would start with the 0. We would then have a 1. Then we'd have, so I'm going across here. So it's going to be 0, this will be 1. Then we'll have a 0, and then another 0, and then another 0, and then another 0, and then we have finally 2 1s. 1 and 1. And this here is the value 67 and the base 10, where this is the most significant bit first, and we could agree to do either way. Just like I say 67, I give the most significant digit first. If we had a custom where we always said the least significant first, like 760, as long as we all went with that same rule, we could communicate, though it does sound strange and gets confused with what we would interpret as 670. So we will use this order, though just be aware that in digital systems there are both conventions, sending the most significant bit first or the least significant bit first, and they actually use a term big Indian, where they're actually spelling it E-N-D-I-N-A, or little Indian. And this actually comes into play, factors in when you go to store a number in memory. Are you going to store it in memory in the order where the most significant bit is stored at the higher address or at the lower address? And so anyway, that's well beyond what we're doing here, but if you ever hear those terms, big Indian, little Indian, it has to do with ordering, of just making sure that, big bad things would happen if you saw the number 67 and I meant 6 10s and 7 1s, but you read it as 6 1s and 7 10s, and the corresponding mix-up in the binary, in a binary representation, it would not work. You'd have problems. Yeah, so our sensor now can send this digital word. It's a byte, but in principle it's a digital word that gets sent over to the receiver. And now it only takes not up to 100 pulses, but here I could represent with 7 bits. I could represent clearly 0 to 100 with the precision of 1 degree C. So that's a whole lot better, right? Just sending a minimum of 7 bits would be enough, and that's better than sending 100 pulses. Now there are some constraints here, and you might wonder, wait a minute, how do they know when 1 0 stops? And how do you know if that's 1 0 or that's 4 zeros or any other number of zeros? And how do you know that this is actually 2 1s and not just 1 1? Well, there's more to it than this. And specifically, the temperature sensor and the receiver have to have an agreement of how much time they will spend transmitting and then reading the value of any particular bit. So if they would have an agreement and say, we're going to communicate at 1 millisecond per bit. So that means that I know that on every millisecond boundary there's going to be another a new bit value, and if the digital line that's connecting us stays at the same value for more than 1 millisecond, then it means that I have 2 adjacent place values that have the same digit value, either a 0 if it's low or a 1 if it happens to be high. Now there's one other issue with this, and that is how do you determine when the pulse begins and when it ends. And so I'm not going to go into that now, but if you want to read about it, you could look up asynchronous serial communication. And this is a very standard form of communication where they will send data in this fashion, which is called serial, one digit at a time. And there needs to be some synchronization at the beginning that says this is the beginning of a new digital word that I'm sending, and this is the end. And they actually, what they will do is this digital line will actually stay up at a high value rather than staying at a low like I've shown it. And they always start off with what's called a start bit. So it sits high, idles high, and then they have a start bit where it'll always go low for 1 bit time. And then after that you send the 8 bits. This is where you'd send the 8 bits of data. and then at the end you always have what's called a stop bit, and the stop bit is always high. And so that way there's a scheme. By doing that, you can always synchronize the receiver and the sender. The receiver will look for a start bit where it drops low, and then after that first bit time, then it will read the next 8 bit times and interpret that as the data being transmitted, and then it will look for a value that's high. And if that ever gets violated, then it goes, ooh, error, I'm going to discard that data I just received because something went bad. That's totally out of scope of what we're looking at doing right now, but I thought since I got so close to talking about it, I might as well just mention it. And so for the interested learner, interested student, you can look that up, asynchronous serial communication. Okay, so at this point, what we've established is that, let me go back to the beginning, what were we trying to accomplish here? Binary representation of numerical data. Okay, so what we've established is that just like you can have multiple digit decimal values, we can have multiple digit binary values. And as soon as we have binary numbers, multiple digit binary numbers, then we can start talking about the arithmetic that goes along with that. So I think I'm going to stop here, and then we'll pick up with another lesson where we'll talk about some arithmetic. We haven't yet spoken either of how do we represent a assigned value. Are there such things as negative numbers? How do we encode that with just these digital lumped values of true and false, or 0 and 1?